So the next chapter that we're covering is all about the reaction of alkynes and preparation of alkynes. I will ask that you do some review at home, specifically regarding acid-base chemistry, which is just review from last term, and then nomenclature, meaning naming of alkynes. I'll give you one hint. It's exactly the same as naming alkenes, with what exception? Yeah, it has a YNE suffix, so it's a big loop that we're throwing you for right now. All right, so now let's talk about preparation of alkynes. We're not going to get into the functional groups like that. There's weird priority systems for which one wins out. That gets into nitty-gritty IUPAC rules. So let's do preparation of alkynes first. And luckily, this is all chemistry that we're pretty familiar with. So let's go back and review. Let's say I have this alkene, or sorry, this halogen, right? So alkyl halide. And I treat this with a strong base. So strong bases typically have a negative charge. What sort of reaction will occur? E2, right? We've got a beta proton coming off this methyl group over here. So this base will grab one of these anticoplanar beta protons, clamp down, kick off bromine in an E2 mechanism. And you can use this to make an alkene. In this case, this alkene is styrene. It's the monomer for making polystyrene. The other thing you can do to favor this reaction is run this under high temperature. However, in this case, there's no risk of substitution reactions really occurring because we're using a generic base. All right, alkynes are pretty similar. All right, so let's say that we have an alkyne where instead of one halogen in that position, we have two. So we've got two bromines for this example right there and there. We still have beta protons adjacent to those bromines. And oftentimes what we'll use in this reaction is a really strong base. The most common base that you'll see used is NH2-, or you may see this written as NaNH2. So let's actually write out the whole reagent. This is called sodium amide. It's a really, really, really strong base. It's not a very good nucleophile though. So this will do an E2 reaction and kick off our bromine. At least one of them. We still have two remaining protons coming off that methyl group though. And what do you think could happen next if we have another equivalent of sodium amide around? Do it again, right? So if we have more of this around, this can grab another equivalent, clamp down, kick off our bromine. And we can make an alkyne. One problem with this reaction is typically when you're trying to do this, you use a huge excess of your sodium amide in order to drive both elimination reactions. So what do you think could happen if we have excess sodium amide floating around? I think you're on the right track. So we could potentially attack one of the protons, meaning do an acid-base reaction. Where's the most acidic proton on this intermediate? Is it on the ring or is it the one coming off the alkyne? Off the alkyne, right? So if you remember, protons coming off of sp hybridized carbons are unusually acidic due to orbitals being shorter. So if we have excess, you'll end up making this anion, where this carbon on the end now has a formal negative charge. All right, so now we got to get into some of the naming. The starting material that we were working with had two halogens coming off of the same carbon. This is called a geminal dihalide. And then the alkyne that we made and deprotonated, this is now called an acetylide ion. Typically, we don't want to isolate our anion. We want to isolate a neutral compound, but there's a pretty simple solution to this. What could we do? Probably just throw a proton back on using a separate reagent, right? So in our last step, oftentimes what we'll do is just treat this with some sort of weak acid. So for example, you could use water as a source of weak acid, and in this final step, you can reprotonate to get your terminal alkyne, meaning return that proton to that original position. Why do you think I'm calling this a terminal alkyne? Yeah, it's on the end, right? So a terminal alkyne means that you don't have carbons coming off of each side. You've got a hydrogen off of one side and some sort of alkyl group off the other side. It is important to note that this second step is necessary for terminal alkynes. Do you think you need this second step for internal alkynes? Yeah, that's a good guess. Why don't you think we need it for an internal alkyne and only a terminal alkyne? Yeah, we don't have a proton to deprotonate if we've got an internal alkyne, so that second step's kind of unnecessary for internal alkynes. But it's kind of a clever way of doing a double E2 reaction to form some sort of alkyne. Yep.
So, but don't we get a terminal alkyne before we get to the acetylene ion?
Yeah, the problem is, like we were saying up here, you typically run this in such a huge excess of your base that that final deprotonation is uncontrollable.
Okay.
So it's like we're purposely overshooting the reaction, and then we have to reprotonate it at the very end to isolate our neutral product. Good question, though. All right. So there's another method that you can do as well. It's a variation of this. So let's take a look at the other method. What if we have two halogens that are adjacent to one another? Instead of being called a geminal dihalide, these are called vicinal. And if you react this with excess base, and we indicate that it's excess typically by writing EX or just XS afterwards, we can do the same thing, a double E2 reaction, quench with water, and we can make our terminal alkyne. So both of these reactions are really good, clever ways of doing a double E2 to make some sort of alkyne. It can be either an internal alkyne or it could be a terminal alkyne. It just depends on the starting material that you're using. Does that make sense? All right, so we're gonna jump straight into reactions, but luckily these are pretty straightforward reactions. Sorry, I'll go back. Please yell at me if I'm going too fast, and I'll make sure I slow down a little. I get so excited about all this. Yep.
So with adding a group on the end instead of like a hydrogen, can we do like a methylbromine or something?
So we'll cover how to do that later. So you're correct. With the acetylide ion, you have a negative charge there that can be a really good nucleophile, and you can use that for SN2 substitution and actually add carbons on. But we'll cover that a little later in this chapter. Yeah?
You said that the reaction is the same for both of these?
Yeah, so if you think about the bromine on the left-hand side, right? It's got a beta proton right here. So these two can do an E2 reaction. If we think about this proton right here, this is beta to that one. So you can do sequential E2 reactions and essentially get to the same product, right? So just one E2 after another. Whichever one you do first doesn't really matter because you're purposely going to overshoot it anyways and make your alkyne. Yeah, good question though. All right, so the first reaction we're going to cover is actually very similar to the last reaction we covered last chapter. And we're going to talk about reduction. So let's review a little bit. We saw reduction of alkenes where we can go from a double bond to a single bond. And what reagent did we need? Yeah, we needed hydrogen gas, and we needed some sort of catalyst. Oftentimes it's palladium on carbon. Sometimes you just see platinum. Doesn't really matter. You can even use Wilkinson's catalyst, that one with ruthenium if you want. The key thing with this is you do syn addition of hydrogens and you convert a double bond to a single bond. You can do this with alkynes as well. Okay, so with alkynes, let's say that we've got this internal alkyne, meaning we've got a methyl group coming off of both sides. We could treat this with hydrogen and a catalyst. We can actually use the same catalyst as before. And what will happen is you'll add 2 hydrogens in a syn orientation like this. However, you can't stop here. So I'm just going to put brackets around here and say it's impossible to stop here. And the reason it's impossible to stop there is that alkene is actually more reactive towards hydrogen than your starting alkyne. And so if you have additional hydrogen around and palladium on carbon, what do you think you'll get out at the very end? Yeah, you'll just get your alkane. So with hydrogenation of alkynes, you can overshoot and go straight to an alkane, which is pretty nice. However, it kind of depends on the situation. Sometimes as a chemist, you might want to stop at that intermediate. So go from an alkyne to an alkene. And let's talk about some workarounds to avoid that impossible intermediate for this traditional hydrogenation. That's a good question. So we'll talk about cis versus trans for that intermediate. We can actually control that by using a few tricks. All right, so the key to stopping at that intermediate is using something called a poisoned catalyst. All right, so basically you're going to kind of hinder the catalyst so that it can't do that second hydrogenation and get you to your alkane. And our goal is to stop at that intermediate alkene. So let's take a look at what goes on in a poison catalyst system. The first one is called Lindlar's Catalyst, named after the chemist that helped develop it. And this is a catalyst that's kind of a cocktail of a bunch of different things. First thing you have is this aromatic heterocycle. Then you've got a metal catalyst that's palladium and barium sulfate. And then typically you run this in some sort of alcohol solvent, maybe methanol. However, most people, when they look at this, they just call it Lindlar's Catalyst. So that's a good question. In order for this to be a true active poison catalyst, you have to mix that aromatic heterocycle with that metal, with the barium sulfate. It'll form this inorganic complex that will then do the hydrogenation reaction. It's a bit weird, but like I said, if I ask you to provide a reagent, it's perfectly okay to write Lindlar's Catalyst and avoid having to draw out the heterocycle and all that stuff. Yep.
This is used in conjunction with hydrogen gas?
It's used by itself, so you actually don't need hydrogen gas for this to work. Yeah. Or actually, I take that back. Holy cow. You do need hydrogen for this one. I'm thinking of another one. So you need H2 gas for this as well. Let me just write that separately. So plus H2 gas. There are other reducing systems where you don't need additional hydrogen. We'll talk about those in a second. So that's the first one. The second one's referred to as the P2 catalyst. And P2 catalyst also requires additional hydrogen as well. And that's a nickel boron complex. So it's Ni2B, and that one works as well. However, more commonly, you'll see Lindlar's Catalyst used. It's just historically the go-to for most organic chemists. Does that make sense? All right, so I'll show you an example of this. So the example is, let's say we have that same internal alkyne. We can react this with H2 and Lindlar's Catalyst. And when you react these together, like I said, you'll stop at the alkene and you'll get syn addition of your hydrogens. Oops. Does that mean we're going to make a cis or a trans alkene? Yeah, we'll always get our cis alkene. We're not really going to go into the reaction mechanism for this. It's somewhat complicated. It's something you might cover in advanced organic chemistry. All right, so maybe there's a situation though where you don't want the cis alkene, but you'd rather have the trans alkene. If you want to do that, you have to use a different reagent. So for trans alkenes, you must use dissolving metal reduction. And this is the one where you don't need any additional source of hydrogen. So I'll show you this one as well. We'll actually cover this reaction a bit more when we get into radical chemistry. But let's say we have this internal alkyne that we were working with before. In order for this to work, you need elemental sodium. To indicate that it's elemental, you'll often see a little not sign in the top indicating that it's not a cation. It's just the metal sodium. And then you're also going to have ammonia as your solvent. So we put liquid in quotation marks, so you can have an L in there to indicate that it's in the liquid state, not the gas state. And in this reaction, you can also make an alkyne, alkene, but this time it will be anti-addition. This actually goes through a radical anion intermediate. We haven't even talked about radicals yet, so we're going to kind of talk about this later when we get into radical chemistry. So this will give you the trans alkene only. So we've got a lot of tools at our disposal to now interconvert between alkenes and alkynes if we want to. So let's make a brief map. All right, so we said before that we can start out with this internal alkyne. We can go straight to an alkane by using hydrogen and palladium on carbon if we wanted to. Conversely, we can stop at the cis alkene, and that was where we needed H2 in Lindlar's Catalyst. And we said if we wanted to go to our trans alkene, we needed that dissolving metal reduction. Dissolving metal reduction is where we use elemental sodium followed by ammonia, and we can get to the trans alkene. Conversely, if we want to convert either of these to the alkane, what can we do? Yeah, H2 and palladium on carbon would work for either of these systems. Hydrogenation of alkenes doesn't matter. It'll still give you the same product. So now we've got a whole set of different ways of doing various reduction reactions. The reality is there's even more than these available, but we're going to stop at that. These are kind of the classic reduction reactions for alkenes and alkynes. All right, I think that's where we're going to stop today. Yeah.
So with that reagent of the sodium,
Yeah.
Is it just so small enough chunk where it dissolves into the?
Yeah, so the sodium will actually dissolve in the ammonia. That's why it's called dissolving metal reduction. Yeah.
Okay.
Yep.
So is this 3 of the reactions that we're gonna have to know, or
Yes, we'll need to know all of these reactions for the remainder of the year.
okay, so it's 3 of the 69.
It's what?
It's 3 out of the 69.
Yep, exactly. So it's 3 out of the 69 reactions. All right, if you want to get started on your problem of the day, we still have a few more minutes. I would recommend trying to get started on it sooner rather than later.
So would the P2